Okay, the next section in the textbook that we're going to cover is the self-ionization of water. We're actually skipping a couple of sections in the textbook about acid strength and the molecularity of acids, and going to the self-ionization of water. Okay, self-ionization is a generic term that means two of the same molecules react to give ions. So water is the most popular one here. So I have two waters in an equilibrium to give H3O plus and OH minus. This video here, which I gave you the address here, so if you want to go back and watch it on your own, you can. And I don't know if it's going to allow me to point there. No. Oops.
Self-ionization is the process in which two like molecules react to give ions.
Okay, it already passed it. Now let me go back to about 1 second. Okay, so I had this circled on the slide. I want you to notice that this is a hydroxide and this is a hydronium ion. And watch what happens as these two molecules here move forward.
In which two like molecules.
So now you see that this one has become, this was the hydroxide and it's become water, and this one has also become back to a water. So that was it going in reverse.
React to give ions. Water undergoes a self-ionization to form hydronium ions and hydroxide ions. The react
Here, this one passed from hydroxide to water. So it had a hydroxide here and a water here, and it became that. So it's not just the fact that a water becomes hydroxide. Basically, the hydrogens are being played either direction.
Maintains a steady
And that one just passed
concentration of each of these ions at 1 × 10 to the -7th molar under neutral conditions. The product of these concentrations is the ion product constant for water, Kw, and is equal to 1 × 10 to the -14th at 25 degrees Celsius. Self-ionization.
Okay, so that's showing that reaction there. And they mentioned in the video the self-ionization constant for water. Because it's an equilibrium, it has an equilibrium constant. So if this is the reaction, and I just combine the two waters together, it gives me hydronium ion and hydroxide. So if I were to write out the equilibrium constant expression from last chapter here, Kc would be the hydronium over the hydroxide. Why do I not include the water? Because it's a liquid. So when I first introduced equilibrium constants, I introduced the fact that we were going to change what the subscript was. Well, we're going to put it as Kw for water. It's the same formula, and it's a constant 1 × 10 to the -14th. This is a number that you must memorize. Oops, not that color. Okay? So you need to memorize this number. It's not given to you anywhere. And that is equal to the Kw of water. So now, if I know either the concentration of hydronium or hydroxide, I can, and the ion constant for water. Okay, now this is at 25 degrees, but all the problems that I will give you are at 25 degrees. If it's not 25 degrees, then the Kw will have to be given to you. So I only expect you to know the Kw at 25 degrees. So it asks the question, what are the hydronium and hydroxide concentrations for each of the following? Well, it's not just giving me one. I have to find both of them. Okay. So the first question to ask yourself is, sodium hydroxide here, is this an acid or a base? And this is a base. And that's important because as a base, that means that my hydroxide ion concentration is the molarity times the number of OH minuses. So in this case, it's 1.55 times 1 to be 1.55 molar. And then I go back to the other formula, which I'm going to write here at the top. Kw, which this is given to you on the exam, is H3O plus times hydroxide So for this particular problem, I have 1 times 10 to the minus 14th. H3O plus is what I don't know, times 1.55. So I divide both sides by 1.55, so I have 1 times 10 to the minus 14th divided by 1.55 is equal to the H3O plus concentration. When I divide those, I get H3O plus is equal to 6.45 times 10 to the minus 15th molar. Okay. I want you to take a second and try to do the next one. Okay. All right, so you ask yourself, is strontium hydroxide, is that an acid or a base? And it's a base. And so because it's a base, the hydroxide ion concentration is the molarity, 0.15, times the number of hydrogens, or no, I'm sorry, number of hydroxides, which in this case it's 2. Because I have a parentheses around this, there's 2 hydroxides there, so this time my hydroxide ion concentration is 0.30. I'm going to plug it into that top equation. 1 times 10 to the minus 14th is equal to H3O plus times 0.30. Divide both sides by 3.30, so 1 times 10 to the minus 14th divided by 0.30 is equal to H3O plus. So my H3O plus for this one becomes 3.33 times 10 to the minus 14 molar. All right, moving on. Now, again, first question, is this an acid or a base? This one's an acid because it starts with a hydrogen. That makes it an acid. So this is an acid. However, the H3O plus, which means that because it's an acid, I get the H3O plus. It's still the molarity, but this times the number of hydrogens. So it's going to be 0.056 times 1 to be 0.056. I'm still using this top equation, Kw. So 1 times 10 to the minus 14th. This time it's the hydronium I know, 0.056. It's the hydroxide that I don't know. So I'm going to divide both sides by the 0.056. So 1 times 10 to the minus 14th divided by 0.056 is equal to OH minus. And so my OH minus is 1.79. Oops, 0.79 times 10 to the minus 13th molar. And the last one, again, first question, is this an acid or a base? It's an acid. The hydronium ion concentration then is 0.47 times 1 to give me 0.47. And my 1 times 10 to the minus 14th is equal to 0.47 times my hydroxide ion concentration. Divide both sides by the 0.47, so 1 times 10 to the minus 14th divided by 0.47 to equal the hydroxide ion concentration. And when I did it, I put in an extra 0, so let me redo it. 1e to the minus 14 divided by 0.47 gives me 2.13. Molar. Okay? And that will be the end of this video.